Chile faces a recurring crisis every summer, one that grows more devastating with each passing year. Over the last decade, the country has recorded more than 67,500 wildfires, destroying over 1.2 million hectares of land. Most alarmingly, 99.7% of these fires are caused by human activity, meaning they are preventable or at least containable if detected early enough. The National Forest Corporation, CONAF, reports that the critical months are December, January, and February, when temperatures soar and humidity drops. As the Center for Climate and Resilience Research, CR2, and the University of Chile document, we are facing a systemic emergency. Most recently, in January 2026, a record-breaking heatwave triggered severe outbreaks that tested our resilience to the limit. The synergy between human negligence, prolonged drought, and relentless winds creates the perfect storm. This is where technology must intervene. By leveraging the Ultralytics platform, we can transform these critical challenges into real-world solutions, deploying AI models capable of early detection when every second counts. Before coding, I reviewed the state of the art and the findings were eye-opening. Top models report impressive metrics, but they all share a critical limitation. They rely on massive datasets and months of work by full research teams. My goal was to determine the performance of a hybrid dataset built from scratch, relying solely on the integrated end-to-end workflow of the Ultralytics platform. I built a hybrid dataset using public sources with open licenses, maximizing time efficiency. The Ultralytics platform allows direct video uploads, automatically converting them into frames at 1 frames per second. Without manual pre-processing, I had thousands of frames ready for annotation in seconds. With only 1,272 images and 2,008 annotations, I tested the platform's true power against massive scale studies. The outcome: a precise dataset with 1,223 fire labels and 785 smoke labels ready for benchmarking. Labeling is one of the biggest bottlenecks in any computer vision project. It costs time, money, and introduces human error. To solve this, Ultralytics platform provides 2 complementary tools that speed up the entire workflow without leaving the same environment. First, I use smart annotation with SAM3 to segment complex objects with high precision through intelligent clicking. This was especially useful for the smoke class, since smoke has no clear boundaries and is difficult to outline manually. Instead of annotating from scratch, the platform suggests the contour and I only validate or correct it. Then, I trained a fast baseline model and used the predict feature to trigger a massive auto-labeling process. In this stage, the model itself generated annotations to accelerate dataset creation, reducing hours of manual work to just seconds per batch. The combination of both tools was essential. SAM3 gave me precision for complex shapes, while Predict gave me scale to label the rest of the dataset. Everything happens in one integrated workflow, with no data exports, no software switching, and full control over the process. Right here, I have new unlabeled images. Notice that when activating the Smart option, Ultralytics lets us choose between official models, like the powerful SAM3 for segmentation, or, as I'm doing now, selecting my own pre-trained baseline model. It's truly impressive how, by using the predict feature, the system automatically labels fire and smoke as if by magic. With the dataset ready, I moved on to the stage that mattered most for this benchmark: training multiple models and comparing them under the exact same conditions. Ultralytics Platform offers different cloud GPUs, from options like the L40 up to the H100, with transparent pricing and no hidden markups. That allowed me to run training on serious infrastructure without having to set up my own servers. I trained 4 models with exactly the same configuration, the same dataset, the same split, and the same 100 epochs. The immediate observation is clear. All the small models stayed in a range between 57% and 62% MAP50. That makes sense when working with a relatively small dataset, where reaching very high metrics is much harder than in studies with hundreds of thousands of images. But the goal of this benchmark was not just to get the highest number. What I wanted to answer was something more important. Under the same experimental conditions, which architecture extracts the most information from the same data? And the best result came from YOLO26s, with an MAP50 to 95 of 37.7%, which is the more demanding metric because it evaluates performance across multiple IOU thresholds. As a NMS-free next-generation architecture, its advantage is not only in peak MAP50, but in consistent performance across thresholds. And that is exactly what you want in an early warning system, where missing critical detections is not an option. With the YOLO26s model selected, I reached the stage that gives the project real-world value: deployment. In wildfire scenarios, especially when drones operate in areas with no network coverage, the platform allows me to export the model with a single click into 17 validated formats, including TensorRT, ONNX, and TF-Lite, making it ready to run natively on edge hardware, such as the drone itself or other embedded devices. For early warning systems with connectivity, such as watchtowers or IP cameras, the most powerful option is cloud deployment. Ultralytics Platform lets you deploy the model to a dedicated endpoint distributed across 43 global regions, with no need for your own infrastructure or manual server setup. You simply choose the region with the lowest latency for your use case, and within minutes, you get an active inference URL, protected with bearer authentication and configurable parameters such as confidence, IOU, and image size. And the best part is that deployment does not only run inference, it also gives you real-time monitoring. From the platform, I can see every request that reaches the model and inspect exactly what happened in each call. The logs show events. That means every inference is recorded, every error is visible, and every health check can be reviewed directly. It is production monitoring without having to configure anything extra. Now, I could have shown you the Ultralytics platform interface directly, but that would not have demonstrated the most important point of this video: that the endpoint generated by the platform is a standard REST API, consumable by any external system and adaptable to different devices, from a laptop to an IP camera or even a drone processing data in real time. That is why I built my own web application from scratch. H spinal systems, Wildfire early warning, developed in pure Python with Streamlit. I designed it in dark mode with a minimal interface, built to run smoothly on a laptop while recording the screen, and still remain lightweight enough to integrate with different video or capture sources. The workflow is simple. I upload an .mp4 file or an image. The application processes the frames, sends each one to the Ultralytics endpoint through a post request with bearer authentication, receives the detections in JSON format, draws the bounding boxes with OpenCV, and displays the annotated result in real time. At the end of the video, it generates a downloadable annotated file and a metrics summary, including how many frames contained fire, how many contained smoke, and the overall risk rate of the video. This application does not exist in any paper. It is a functional early warning prototype that can run on any laptop, consume any IP camera or drone that fits the same workflow, and scale nationally as long as the endpoint remains available. That is the power of the full Ultralytics platform workflow. Annotate, train, export, deploy, and monitor. Everything in one place. This project shows that early wildfire detection with artificial intelligence does not require a university lab or a six-figure research budget. What it requires is quality data, a platform that removes technical friction, and modern architectures like YOLO26s. In Chile, where summer is no longer just summer but wildfire season, this matters. And it matters just as much in Australia, the Mediterranean, California, and across the tropical belt, where detection speed can be the difference between a contained incident and a major loss. If you want to replicate this pipeline, the full workflow is there. Annotate, train, export, deploy, and monitor in one place. The platform also supports the YOLO26 and YOLO11 families natively, export to 17 validated formats for edge deployment, and cloud deployment across 43 global regions. And that matters for one simple reason. Ultralytics solves the three biggest pain points in the computer vision pipeline: annotation, training, and deployment in a single workspace, with transparent pricing and no platform markup on GPU compute. Training on H100 PCIe starts at $2.39 per hour, with no surprises. If you are part of the developer or machine learning community, now is the time to create your account and get started. The link is in the description. platform.ultralytics.com. And if you are building for commercial use, make sure to review the difference between the AGPL 3.0 license, designed for open source and academic projects, and the enterprise license, designed for commercial integrations. I am David Hospinall from Hospinall Systems, Chile. This was H Spinal Systems, Wildfire Early Warning. See you in the next video.